Welcome to the lecture 9.1 of Power System Stability. In this lecture, we'll see the concepts of voltage stability and the reasons for voltage stability in detail. Voltage stability is concerned with the ability of a power system to maintain acceptable voltages at all buses in the system under normal conditions and after being subjected to disturbance. A system enters into a state of voltage instability when a disturbance or increase in load demand or change in system condition causes a progressive and uncontrollable decline in voltage. The main factor causing instability is the inability of the power system to meet the demand of reactive power. We will see in this lecture the sensitivity of voltage with respect to reactive power also, and how the stability could be analyzed for different sensitivities of voltages with respect to reactive power. Now, voltage stability problems normally occur in heavily stressed systems. Heavily stressed systems in the sense already if the power carried by the network is about to hit the maximum power carrying capability, whether it's a line or an equipment, there are chances of hitting the voltage instability point. While the disturbance leading to voltage collapse may be initiated by a variety of causes, the underlying problem is an inherent weakness of the power system. Principal factors contributing to voltage collapse are strength of transmission network, and the first one is strength of transmission network and power transfer level. Which means if a line has a specific power carrying capability or the maximum power carrying capability, and at present the line is carrying some power which is already near to the maximum power carrying capability, then the receiving end bus voltage or the receiving end bus to which this line is connected, the voltage of that particular bus is vulnerable with respect to the sensitivities in or variations in active power transferred by the line, which means for small increase in power carried by the line or active power transferred by the line itself, the voltage profile of the receiving end bus may go down drastically. The second thing is generator reactive power or voltage control limits. We know that every generator, if it's a synchronous generator, there is a reactive power limit based on the field current control. There is a field current limit for the field itself. So the present operation of the present operating point of the generator is very important with respect to how much is the voltage control limit, to what extent the voltage control limits can be achieved. Now, load characteristics. Loads can be of different types. It can be constant impedance load. It can be constant voltage loads. It can be constant power loads. It can be voltage dependent loads. Then it can be zip loads. Zip load in the sense impedance, current, and active power. So loads can be of many types. Suppose if it's a voltage dependent load, then if voltage reduces, accordingly the power is affected. The power that is received by the load or the load demand in terms of power is affected. So based on that also voltage stability could be analyzed. Voltage stability analysis can be different according to different types of loads. Now the characteristics of reactive power compensation. Reactive power compensation devices can be fact devices or even capacitor switching. Switching by means of switching of capacitors. In these cases, we have a maximum reactive power compensation limit of any device. So the characteristics of this reactive power compensation limit also causes the voltage instability. Now, action of voltage control devices such as transformer underload tap changes. We will see this in detail. The transformer underload tap changes, how they affect the stability. This we'll see. Now consider a two-terminal network. We have a two-terminal network here where the sending end voltage is ES and the receiving end voltage is VR. Now the line complex impedance is given as ZLN angle theta and the load complex impedance is given as ZLD angle phi. Now the complex power received by the load is given as PR plus JQR. Now the current carried by the line is I bar. Now this is the Thevenin equivalent circuit where the Thevenin equivalent voltage is the sending end voltage and the Thevenin impedance is this one, ZLD, the load impedance. Now let's see the expressions for voltage and current. So let's see the expression for current first. Current equals ES divided by line impedance plus load impedance. ES is the sending end voltage. Now the line impedance equals, it can be represented in polar form as ZLN angle theta. It is already given here. Now ZLD can be written as ZLD angle phi. ES equals ES angle 0. This is the reference voltage. Now let's see this. Magnitude of I could be defined as from here. So we already know that this is ES divided by this one. ES divided by magnitude of ZLN plus magnitude of ZLD or magnitude of ZLN plus ZLD. Now we take it like this. Magnitude of ZLN can be written as ZLN in the polar form can be converted to rectangular form as ZLN into cos theta plus J sin theta. Then ZLD in the complex form can be converted to rectangular form as ZLD into cos phi plus J sin phi. So when you take this cos theta plus J sin theta and cos phi plus J sin phi, when you multiply with ZLN and ZLD, you will get the magnitude in the denominator as root of ZLN cos theta plus ZLD cos phi the whole squared plus ZLN sin theta plus ZLD sin phi the whole squared. Basically the sine terms are taken together and cos terms are taken together. Now when we simplify this, what we obtain is ES divided by ZLN divided by root of 1 plus 2 ZLD by ZLN into cos theta minus phi plus ZLD by ZLN the whole squared. Now this denominator we are going to represent as root F or F. Root F, we are representing this as root F. So 1 by root F into ES by ZLN. Our numerator is ES by ZLN divided by root F. So this is F. So F is defined here. F is 1 plus ZLD by ZLN the whole squared plus 2 into ZLD by ZLN into cos theta minus phi. Let it be equation 3. Equation 2 is this one. Magnitude of phi equals 1 by root of F. Now why we are doing this, we'll see. Whenever the load is increased, how the voltage profile is affected. We want to analyze this. We want to analyze the variations of voltage, receiving end voltage for variations in loads. Suppose if the load is represented as impedance load, then that is ZLD. So variations in ZLD, how VR is varied for variations in ZLD. If we want to analyze this, we need this expression. So we are somehow trying to relate ZLD and VR. Of course, ZLN is coming into picture because ZLN is the line impedance, and whenever the current through the line increases, I into ZLN drop increases. That will also that will also cause reduction in voltage profile, receiving in voltage profile. So this is represented, this is denoted as equation 4. Now, what is active power at the receiving end? PR equals VR into I cos phi. That is PR equals ZLD by F. See here, we know that VR equals here ZLD and ZLD 1 by root F into ZLD by ZLN into ES. So we are going to substitute it there. Here ZLD by F into ES by ZLN the whole squared into cos phi. This is what is PR. Okay. Now So basically ZLD by F into ES by ZLN the whole squared is VR into I. Okay, into cos phi. This cos phi is here itself, here also. Okay, now we'll see the variations of VR by ES versus ZLN by ZLD. Here, VR by ES, VR by ES divided and ZLN by ZLD. So what is VR by ES? VR by ES in the sense we are trying to represent the receiving end voltage in terms of the sending end voltage. That is what is VR by VS, or the percentage of receiving end voltage with respect to sending end voltage. We know that if there is a drop, then VR is less than ES. If 80% of the sending end voltage is only available at the receiving end voltage, receiving end voltage, then 80% is VR by ES. Okay, so that is what we are trying to correlate. Now, so three things we are going to plot: VR by ES versus ZLN by ZLD, then PR by Pmax. Pmax is the maximum power carrying capacity, maximum power transfer capacity, that is Pmax. This is the actual receiving end active power or the active power received at the receiving end or at the load side, versus ZLN by ZLD. Now I by ISC versus ZLN by ZLD. We'll see now how to analyze this plot. Okay, so the same figure we are taking, ES is the sending end voltage, I is the current carried by the line, ZLN is the ZLN angle theta is the complex line impedance, and the receiving end voltage is PR. Then the complex power received by the load is PR plus JQR, and the load impedance is ZLD angle phi. Now let's see the plot once. In the plot it says ZLN by ZLD versus different parameters. Different parameters in the sense one is I by ISC, another one is PR by Pmax, and another one is VR by ES. So now you can see here, if ZLN by ZLD increases, what happens? ZLN by ZLD increases, you see that VR by ES is decreasing.